Do, do, do. All right, well, I'll begin with reading some scripture here. So this is Psalm 37, verses 5 through 8, I think. Here's how it goes. Commit your way to the Lord. Trust also in him, and he will do it. He will bring forth your righteousness as the light, and your judgment as the noonday. Rest in the Lord and wait patiently for him. Do not fret because of him who prospers in his way, because of the man who carries out wicked schemes. Cease from anger and forsake wrath. Do not fret. It only leads to evil doing. So that's my verses for the day. I will begin with a word of prayer. Dearly Father, we thank you again for your creation and our opportunity we have just to study it and understand it. And I just pray that you'd give us understanding this day and help us to glorify you in what we do learn. In your name I pray, Lord Jesus. Amen. All right, so let me just start class by just a quick review here. If we have a frame of reference, S, right? And usually I think of that as like the Earth frame, pretty much, all right? And then we have a moving frame of reference, which I'll say X bar, Y bar, something like that. Oops, let me write this up here. The S bar frame, right? Then we can talk about the origin of the moving frame of reference, and we can measure the position relative to the Earth as equal to the position of the origin of the moving frame plus the position relative to the moving frame, right? So again, this is position relative fixed frame of Earth, let's say. Now that's just, obviously that's an abuse. Is the Earth a fixed frame? No. But here is the position of origin of moving frame, possibly accelerated. And this here is the position relative moving frame. All right. And in terms of, applied word problems, ones we're actually going to put numbers to and stuff like that, we're not going to think about rotating frames of reference, right? We're just moving them in a linear fashion. So the mathematics here is simpler. We can just differentiate these. And the essential assumption is that the vector basis itself, the x hat, the y hat, the z hat, we're using the same x hat, y hat, z hat to set up the displacements for both of the coordinate systems. That's the fundamental assumption here that makes it like way less complicated than that other section in my notes you're not required to know. If I differentiate this with respect to time, I get that the velocity in the S frame is equal to the velocity of the origin of the moving frame plus the velocity relative to the moving frame. And then if I differentiate it again, I get the acceleration relative to the Earth is equal to the acceleration of the origin plus the acceleration measured with respect to the moving frame of reference. So these are your go-to equations. These are what we want to understand. Now, principal application here would be to apply Newton's law. Now we can apply Newton's law in a inertial frame of reference. All right? So approximately speaking, the fixed frame of Earth is an inertial frame of reference, and there we are well within our rights to say that the mass times the acceleration with respect to the Earth frame of reference is equal to, well, the net force. All right? It's equal to the net force, but that's also equal to the mass times the acceleration of the origin of the moving frame plus the mass times the acceleration measured relative to the moving frame. And so this handy-dandy formula right here allows us to solve a certain variety of relatively uncomplicated problems, like the elevator problem. So let's talk about the elevator problem. Again, example 1. So here's the deal. We've got an elevator. We'll put the origin down here, all right? So essentially this is, you know, I guess we could use, think about basically vertical, right? So why not is essentially the origin, all right? And if you've got, you know, some bear or dude or whatever, you know, something. What do you guys want me to put up here? A bat. A cat. All right, I'll go with a cat or a wombat. They look the same in my drawing. I guess this is clearly a cat. There you go. So you got a cat on a scale. All right, let's suppose that the mass of the cat is m. All right. And so this is what I'm trying to draw here, maybe not successfully, is that this is a, you know, it's an elevator. So you know, it can go up or down, all right? And so I have 2 different frames of reference I can think about, right? I can think about like the Earth frame of reference down here, let's say, S, and I can think about the frame of reference which is co-moving with the elevator, right? And if I think about the co-moving frame of reference, right? What is the acceleration of the cat in the elevator? What can you tell me about the position of the cat in the elevator? It's what? It is constant, right? We're not letting the cat run around in there. He's just standing on the scale. I'd say like a good cat, but I know that doesn't make sense. So, but my point to you guys is that, oh, see, you guys, don't let me do that. What am I missing? No, these got units. The units are all there. Yeah. The units are in the A and the M, but here we're missing a bar. All right, so the bar. No, the units are there. They are in the variables. So anyway, so here, the acceleration of the cat, right? And do we need vectors for this problem? We don't really need vectors, right? It's a one-dimensional problem. So we can forgo the vectors and just think of this as a scalar equation. That's fine. But we do need to decide a direction. So which way do you guys want to make positive direction? How about up? All right, good choice. So we're going to make up the positive direction. But certainly the acceleration of the cat relative to the elevator frame is 0, right? It's 0. So what equation governs the motion of the cat? Well, see, this equation right here, Newton's second law. But then the question really is, what is the net force on the cat? See, that's the thing we need to think more about. We all know that there's gravity, right? There's gravity on the cat. So that's one. And I'm gonna draw the forces like here. I don't know where you want me to draw them. It's easier if I draw the cat as a dot, but I'm just gonna put them like right here where you can see everything. So on the one hand, we've got mg, the force of gravity acting down, right? That's one force that's acting on the cat. Is that it? That's not it, right? If that was it, then the cat would just be falling. But why is the cat not just falling? It's in the elevator, which means its evil little paws are on the scale, right? And the scale is pushing back up with what we call the normal force or the contact force. So, but for the sake of this problem, I'm going to call it the scale force. Scale force, all right? And so the net force here for this problem, so what we got? We've got, let's see here, the F net then, the net force is going to be what? F scale minus mg. Now why minus? Because gravity goes down and the scale goes up, right? All right, so what equation links all this stuff together? So we've argued that for this problem, this guy is 0, right? So the way this all works is that what we got then is that the scale force minus mg, right? That's my F net. That's equal to what? M times the acceleration of the elevator. And so this is how we have to solve these kinds of problems, right? In particular, you could solve for F scale, and that would tell us all kinds of interesting things. So like the scale force has to be mg plus ma naught is what we derive here. I don't just write that down though, right? I understand how that is logically deduced from Newton's second law applied to an inertial frame. Now, once you know that, you can answer a variety of questions, right? For example, let's suppose that the mass of the cat is 15 kilograms, but let's suppose that the scale is such that it says that the mass, it says 10 kilograms. So does that make F scale equal to 10 kilograms? Like, how does a scale work? What does a scale do? Depends on the kind of scale you got, right? If you got one of these American scales, it'll tell you the number of pounds, right? And pounds would be a weight, but kilograms is not, right? So what goes on here is that we have to understand that if the scale is telling us 10 kilograms, that means that the scale force is actually what?
98.1.
So this would say F scale is equal to 98 newtons, right? 10 kilograms times 9.8. Now you say G is 9.81. More power to you. But I use 9.8. Okay. I'm tempted to make it 10. It would make my life easier, but it's not accurate. Anyway, so 9.8 meters per second squared will work for us in here. And so that 10 kilograms times G, that gives me the actual weight which is put on the scale, right? Anyway, that's the force with which the scale is pushing back. If that's what it reads, that's the force that the scale is putting on the cat. And so that being the case, we can ask the question, okay, then what's the acceleration of the elevator? Right? That's a question we can ask now. So okay. What's the acceleration then? What's the acceleration of the elevator? Well, let's figure it out. So we've got ma naught is equal to the scale force minus mg. And so what you're looking at is, let's see here, so I've got 15 kilograms times a naught is equal to, now it's kind of silly, right? I could have forgone the multiplication by 9.8 if I just, bided my time a bit here. We could have, anyway, okay, so I'm fine. We'll just put the numbers in. So what's mg? 15 kilograms times 9.8 meters per second squared. So apparently a naught is equal to, 98 newtons minus 15 kilograms times 9.8 meters per second squared. I regret putting numbers in. This would have been easier if I'd kept it algebraic, right? Putting numbers in the problem almost never makes it a better solution. Almost never. But there it is. So 98 minus 15 times 9.8 gives you minus 49. Divide that by 15. I get minus 3.26. Now my question is, does that make sense? if the cat feels lighter than it actually is, does it make sense that the elevator's dropping? It does, right? Extreme case, if it was free falling, the cat would be weightless, right? And the equations start being hard to interpret if your acceleration is more than minus g, right? If a naught's like minus 2g, and you're still imposing these equations, what are you saying? You're saying that the cat's feet are somehow glued to the scale, and the scale is literally pulling it down as the elevator drops, right? I mean, I'm not opposed to it. We could glue the cat's feet to the scale.
Are like nailed to the elevator floor?
That would be what we were saying if we impose these equations in that kind of regime. Yeah. But maybe we got some Velcro tape and we got the scale Velcro down or something. I don't know, whatever.
Do we need to like impose like almost like a domain for functions, so it's like if you start getting these answers and you need to formula?
We always have to keep in mind what's physically reasonable. Yeah. Yes?
Why would be a 9.8 algorithm?
9.8 is always positive for us. So g in this class will always be 9.8 meters per second squared. I do not put a minus in g. G is this number. Or, what was your name? Gabriel. For Gabriel, 9.81. Right? No, I mean, it's fine. Some books have like 9.79. It kind of depends on where the book is, published, right? Like gravity does vary a little bit depending on how far you are from the equator. Okay, so next up, we could talk about this little relative velocity problem, example 2. So here I have a river with a speed of 0.55 meters per second. All right, so here's river. And the river has a speed, the velocity of the water, 0.55 meters per second. All right, great. And I say a student swims up the river a distance of 1 kilometer, all right, and then swims back to where he began. So let me draw a picture of that. So my pictures are always kind of dumb, but they're just to organize my thinking. So you got a swimmer, he starts here, right, and then he goes up here, and then he comes back, right? And supposedly that distance he went was, what, 1 kilometer? Is that what I said? So 1 kilometer upstream, and then he swims back. So then the question is, if the student can swim 1.1 meters per second in still water, then how long did this swim in the river take? So velocity of swimmer, 1.1 meters per second. Now, so this is understood to be relative to the water, right? Obviously, right? So basically we think of the water as a kind of moving frame of reference, all right? Anyway, let me not overcomplicate this. There's 2 cases to think about, right? So when he's swimming upstream, when he's swimming with the water, what's his velocity relative to the earth?
1.65.
So going in direction of river, the speed of the swimmer relative earth. This is really a kind of horrible variable name, but there it is. Speed of swimmer relative to earth is equal to, what is it we got? We got 0.55 meters per second plus what? 1.1. So in short, we've got 1.6, I think you guys told me a second ago, 1.65 meters per second when he's going with the water, right? And then, what does he do? He turns around and he swims back, right? And so the velocity return trip, right? Return trip, we've got the velocity of the swimmer relative to Earth equal to, how's it go? 0.55 meters per second, minus 1.1. Now, all right, let me not do that. Let's just talk about his speed. So I'm going to keep it positive, all right? Technically, if you wanted to stick with the sign conventions, you'd say it's a negative velocity for the return trip, right? Let me just not do that. That'll weird you guys out if I do it. Let's just talk about the speed. The speed would be, 1.1 meters per second minus 0.55 meters per second. So that would be 0.55 meters per second as it happens, right? Okay, so then how do these velocities go? So we're talking about constant velocity motion both ways, right? So how's that work? We've got 1 kilometer is equal to, let's see here, 1.65 meters per second times t1 plus 0.55 meters per second times t2. Do I know anything else? I must know something else.
Wouldn't it be 2 kilometers in that case? Because it's 1 kilometer down and another kilometer back.
Yeah, you're right.
And we could also break it up into 2 equations, correct? Like 1 kilometer.
Yeah.
And then
So I'm. Thank you. Yeah, it's 1 kilometer up, 1 kilometer back. So yes, I should just divide and conquer. I should do one at a time. I have a way of making things more complicated sometimes with these kinds of problems. So let's just not listen to me. Let us do the more obvious thing, which is just to think about it in stages, right? So the first one, 1.65 meters per second. So we got what? We got 1 kilometer is equal to the time it takes to swim up to the turnaround point. Let's call that T1. So how we go? Distance is velocity times time, right? So the velocity here is 1.65. Now why can I say that? Because the acceleration is 0, right? So we're back to like middle school science stuff, right? Just distance is velocity times time. And so the time for the first leg of the trip is 1,000 meters, that's a kilometer, divided by 1.65 meters per second, right? Whatever that works out to. Likewise, in the return trip, we've got, 1 kilometer equals to the time, equals the time to return times 0.55 meters per second, which tells me that T2 is 1,000 meters divided by 0.55 meters per second, right? So you crunch the numbers there, and what do you get? You get, let's see here. So I believe you get 606.1 seconds for this one, the first one, and 2,424 seconds for the second one. And the funny thing is it doesn't really matter whether he first swims, one way and then the other, or vice versa, right? Because either way, you're going to get the same time. Whether he first swims upstream and then swims back downstream, or vice versa, it's like the symmetry of the problem says it doesn't matter which one comes first.
Isn't it because the river's only going one way?
Yeah, yes, the river only goes one way. That is true. Yeah.
I've got 1,818 for T2.
I also.
Oh, yeah. Thank you. I have looked at the wrong number. So, yeah, see, that number is like right above my, so yeah, what I just wrote down, thank you. Yeah, it's the sum of these two. So to take these, add them together, T1 plus T2 was 24, that's funny. 24 seconds. 2,000, otherwise known as 2,424 seconds.
Final time is-
Yeah. All right, so yeah. So anyway, in summary, to solve relative velocity problems, all you have to do, right, is identify what medium it is that's moving, right? And use the basic rule that velocities add, you know? And use some common sense, right? Like, so if you've got like a moving elevator and you're walking in the same direction as one of, you ever been to the airport with these moving elevators, right? So if you're walking in the same direction as the elevator, then the velocities add, right? On the other hand, if you're walking the opposite direction, it subtracts, right? If you could just walk exactly the velocity of the moving elevator, you could just stand in place, right? If you wanted to do such a thing. You ever see a little kid like walking up the wrong direction in an elevator? Just staying in place, like you can do that too. Yep.
How do you find velocity when you're going perpendicular to the water?
How would you find velocity when you're going perpendicular to the water? Well, it becomes the addition problem, vector addition. You got to use vectors. So if you're, you had a river and suppose you're just always going 1 meter per second that way, and you've got a river which is going 3 meters per second that way, then your velocity relative to the Earth would be equal to like 3 meters per second, 0, plus 0, comma 1 meters per second. And then you can kind of work it out from there because that's the velocity relative to the Earth, so you can figure out where you're going to go from there using kinematics. But you have to add velocities. So, but if it's if it involves a perpendicular direction, we got to use vectors. Yeah. So that brings me to one of my favorite topics, which is circular motion. And we talked a little bit about it, I guess, but I should talk some more. So I need to derive a few formulas for you guys. Make sure I've anyway, I wanted to spend kind of like emphasize this elevator problem and spend some time on it because I think it's confusing. There's a lot going on here, but it's actually very simple once you understand the rules. And you can always check yourself by, your experience in elevators accelerating. Well, that's not entirely true. You've been using the elevator in DeMoss. It doesn't really accelerate. I don't know what it does, but somehow we get from one floor to the other, but I can't actually feel it moving. Go over to the parking garage. You can feel acceleration over there, right? Okay, so circular motion. Let us discuss circular motion. So I think a good way to revisit this topic is to begin with a vector equation which describes motion in a circle. So what does it mean to go in a circle? If I have, right, the center of the circle being at vector r naught, right? If it's the center of the circle is at r naught, and we want to describe a circle like this, right? So we can talk about a typical point on that circle. Let's call it R. So a typical point goes position R from the origin, let's say. What makes that, put that chair there. What makes it a circle, right, is that the distance, right, from R to R naught is a fixed constant, which we call the radius of the circle, right? That distance is the radius of the circle. Okay? So a circle is the set of all points that are equal distance from the center point of the circle, right? This defines a circle. Okay, great. And a nice thing to do then is to square this equation. Squaring that equation, I can convert it to dot products. All right, great. And once you have dot products, well, this is a nice thing to differentiate because the rules of calculus for dot products are really simple. In particular, this is the product rule for dot products. If you've got the dot product of two functions of time, well, the rule for the dot product is that there's a product rule. So it goes d/dt dot b plus a dot dv dt, right? That's the usual product rule, except the product here is a dot product. All right? Okay, so let's differentiate this vector equation. We can do that. And what we'll have is d dt of r minus r naught. That guy, dot product with r minus r naught, plus r minus r naught, dot product with d dt of r minus r naught. Now, the time derivative of the center of the circle, so we're, for the sake of simplicity here, we're assuming the circle is not moving. Right, so the circle's fixed in place for this discussion. R naught is a constant vector, okay? If that's the case, what's the derivative? 0. Very good. So that makes this 0, that makes that 0, and that makes what's here actually just what? dr dt, right? What's dr dt? It's the velocity. So you've got velocity dot r minus r naught plus r minus r naught dotted with the velocity. And what's this all equal to? What's the derivative of r squared? It's a circle, right? So r is a constant. Derivative of a constant, also known as? 0, right. Aha. So then what? Well, it might be helpful for us to invent yet another letter just to describe what's going on here. Let us say that the unit vector, which points radially out from the circle like this, let's give it, see, I don't know if I did this. Oh yeah, I just called that r hat. Now that's kind of, see, it's bugging me because like technically r hat should point that way. So let me make it a funny looking r hat. So script r hat. I feel better about my day now. So this vector here, we can write as r times funny looking r hat. So, all right. So we've got velocity dot that equals to 0, right? And by the way, the dot product is commutative, so we can just put these together. We've got twice that equals to 0. This equation is not particularly surprising. It says that the velocity of something going in circular motion is what? Let me draw a bigger picture here for us to talk. So here's my circle, right? Let's talk about the motion right here. So the funny looking r hat would look like that. It goes out like that. And if the circle, if the motion is counterclockwise, the velocity should look something kind of sort of like this, right? So no surprise, those are perpendicular, right? That makes sense. All right, what else can we do? How about differentiate again? What happens? Differentiate again, what do we get? So we get, this is a constant vector, right? So if we differentiate this, we just get the acceleration dotted with r hat. Man, I feel like I'm messing something up. Oh, that's not a constant vector. I'm a dummy. Is r hat, funny looking r hat, a constant vector? Is it? As the circle goes around, is this a constant vector? No. So, duh. Differentiate this. We've got dv dt. I'm going to divide by 2. Get rid of the 2. All right. So dv dt dot r hat plus v dot r times, I'm going to write back out what r hat is. Oh, goodness gracious. I'm sorry. I regret my choices. So this, I really should have just left this. I'm flag on the play, guys. So this is just giving us v dot r minus r naught. equals to 0. There's a 2 out here, but we can divide by it, right? Differentiate this. Let us not overcomplicate this. Just differentiate this. We get dv dt dotted with r minus r naught plus v dot ddt of r minus r naught using the product rule. But what this gives me, on the one hand, is the acceleration dotted with, now this is the radius times the script r vector. I'll use it now. So I am going to do that step just now instead of earlier. And this, it gives me v dot v. All right. So finally, the thing I was trying to get us to here, we can see then that the acceleration dotted with the radial direction to the circular motion is equal to minus v squared over r. And so there you go. That's what I'm after here. This simple formula that the radial component of the acceleration must be equal to v squared over r in the center-seeking direction. This is a non-negotiable. All right? If you've got circular motion, this is part of the acceleration. It's inescapable because the calculus gives it to you. So like the part of the acceleration has to be like this. So like acceleration, so this is the centripetal part of the acceleration, a dot r hat, v squared over r. Minus v squared r. So it's inward seeking, opposite direction of r hat. All right, so now I derived something for you guys the other day. Oh, rats. So you notice this derivation doesn't require any kind of former knowledge from another course. All right, this is pretty much, if you know this dot product rule, you can derive this. It's just basic vector and differentiation. However, if you know a little bit more, then you can do what we did the other day, right? I think I just did at the end of class, so let me just review right quickly. And I'll try to be brief here. But we can also take this tact, this view. We can say, oh, the velocity is the speed times the unit tangent. And if I differentiate that, that gives me acceleration. But by the product rule, that gives me dv dt times t plus v times dt dt. But this is the unit tangent, all right? And so what we then have is, if you look at this, what it really is this it's the second time derivative of the arc length, or the distance traveled, times t plus v. And there's something called the Fresnel-Serre formula, which gives you v times the curvature times the normal vector for that. So in short, you get, I'll write it this way, dv dt, that's the change in the speed per unit time, plus v squared over r in the normal direction. So this is another handy formula for the acceleration. This is independent of circular motion, all right? This is just a general rule for acceleration. So here, kappa is called the curvature. The curvature of a curve is 1 over the curvature is equal to the radius of curvature. And again, if you want to know what it looks like, if the curve looks like this, the curvature is if you take a particular point, you fit a circle that just kisses the curve right there. The curvature is like the reciprocal of the radius that just fits into the path, all right? This is so-called curvature of a curve. All right, so long story short, this gives us a general relation for acceleration that gives us two pieces, all right? You see the piece that we've got, so the normal vector, by the way, points normal to the curve. So like the normal vector wanted a better point this way. sorry. Oh yeah. Normal vector points this way. And I mean, if the curve is going this way, then I guess the tangent vector would be like this. Right. So the normal vector points towards the center. So like the normal vector is the opposite direction of the r hat that I've been writing, which is why there's no minus in that formula. However, t and n are perpendicular vectors, right? You guys showed in the homework that the length of a sum of perpendicular vectors is just given how? The square of the sums of the lengths being added, right? So in particular, like the magnitude of the acceleration squared, it's just equal to the change in the velocity, the change in the speed squared, plus, well, v squared over r squared. Or if you like, erase the square, put a square root, there's a formula for the magnitude of the acceleration in terms of the speed, the radius of the curve that it's going around, and its change in velocity. So as we think about circular motion, it's possible that the acceleration is not center seeking. All right? So like if the acceleration, for example, looked something kind of sort of like this, maybe this is the acceleration, all right? That acceleration has two pieces, right? It has a center-seeking piece, and it has a radial piece. The radial, so what does this mean? If circular motion is like this and your acceleration is not center-seeking, that means it's not constant speed. That means there's a piece of the acceleration which goes, like this. So there's this dv dt times t piece, and then the center-seeking part has to be v squared over r. Right? The sum of those two, the vector sum of those two, give you the acceleration. All right. Uh-oh. Sorry. Quick. Hurry. Hurry, Violet. You got it. There's still time. Should I put it back up? Okay, fine. It'll take me a second to get my computer to behave anyway. It always does. It's a rebellious computer. Wasn't the weather cold like 3 seconds ago? I'm feeling hot again.
It's pretty warm. Hot air rises in the middle.
All right, let's see here. All right. Sorry, guys, but the show must go on here. Poor planning on my part. I should have been writing on that board over there. My apologies. So did I ever tell you guys that I don't believe in the flat Earth? Yeah. I think that the Earth is hollow. Yeah. There's like an inside. But the thing is, like all these flat Earth people, they say that there's like this ice wall in Antarctica. It's not true. It's actually a gateway to the interior Earth. You can also get into the interior Earth if you can go under the ocean and the North Pole. There's like a gateway there into the interior ocean. It's actually inhabited by a lost race of Amish people, but they're technologically advanced. They have something called woodtronics. Well, all their technologies have something called woodtronics. It's like the electronics except it's made with the heartwood of a 1,000-year oak. But it can only be harvested in the moonlight, which is tricky in the interior Earth.
Can you be a director? I think you need just a temporary career change. I just want to see this one.
Now you might wonder how I know about this. It's because I am one of those Amish. I can't say any more. I'll be shunned. So anyway, yeah. So I don't know. That's part of the story. I'm still working on it. My brother also has a dream of creating a conspiracy theory and publishing it online, and then my mom telling it back to him, independent of him telling it to her. Our best candidate for this is the McDonald's conspiracy. Did you know that there's a McDonald's in North Korea?
There's no way.
See, it almost makes sense, doesn't it? Yeah. It's not true. There's no McDonald's in North Korea. All right, so the centripetal part of the acceleration center seeking, like that. This is the tangential part. Sorry about I need to find a less bright laser. This one's a little bit much. Joking aside, though, well, here's a circular track race car problem. I don't want to talk about that right now. I want to spend this time talking about the Earth. So let's talk about the Earth. Why is it that the flat Earth folks, one of the things that they tend to say is, you idiots, you believe in gravity, but if the Earth was really spinning, you'd just fly off into space. Why don't you fly off into space? I've seen this many times. And the answer is because gravity's like way, way stronger than the spinny force. Like way stronger. So what is the acceleration due to the circular motion for the Earth, right? The Earth, how long does it take the Earth to spin around once?
24 hours.
24 hours, right? These we call these days. All right, so yeah, so what does that mean? Well, one day is 86,400 seconds. The radius of the Earth is approximately 6,371 kilometers. This was estimated to about 2 or 3% by the Greeks 2,000 years ago. All right, it's been known for a while. We didn't just discover that the Earth is round in the middle. Like ancients knew the Earth was round. This is not a new thing. Anyway, and if you're really going to be literal like that about the Bible, then you should really be wondering where the four corners of the Earth are. If you're going to take this approach, why aren't there four corners? Why is it a disk? I don't get it. Anyway, other things. So the velocity of the Earth, like a point on the Earth going around, would be 2 pi r times divided by 86,400 seconds. Now that is 463.3 meters per second. If you were a professional baseball player and you could throw a pitch 463.3 meters per second, you would be like legendary. That's impossible. That's like, oh, there it is. This is a little bit more understandable. About 1,000 miles an hour. So, I mean, hey, at first glance, we're going 1,000 miles an hour on this, big ball of water in space. Why don't we just fly off? Well, yeah, but the thing is the radius is super huge. And so the centripetal acceleration is only 0.03 meters per second squared, which means that if you were to compare the force of gravity, well, not the force of gravity, but the net acceleration due to so the acceleration that you actually experience, right? It's a combination of gravity and the fact that you're standing on the Earth and the Earth is spinning, right? So you get spun with the Earth. You're experiencing the centripetal acceleration, and you experience more of it on the equator than you would, say, the pole. So at the pole, centripetal acceleration 0, because you're not actually, there's no radial distance from the center of the axis which you're spinning. And the difference is only like 0.03. So that 9.81 you're talking about, that's right in the 9.8 versus 9.81. That's in this kind of issue. How far are you from the equator? How much centripetal acceleration are you experiencing? And then you might wonder, okay, well that's lovely. So about 99.7, so it's something like 99.7% of your weight, well, I have a comparison of the, equatorial weight versus pole weight there. But another thing you consider would be, well, we also have the sun, and we're going around the sun, we think, right? We believe Copernicus. Ptolemy's dead to us. Okay, truthfully, Copernicus and Ptolemy are both dead to us. They've been dead for a while. But the radius of the Earth orbit around the sun is 1 astronomical unit, which doesn't really mean much, but that means 1.5 times 10 to the, 11. Okay, thank you. You guys have better eyes than I have. So 10 to the 11th meters, or like, what, 8 light seconds or 8 light minutes, something like that? I forget exactly. Anyway, the velocity of the Earth relative to the sun, 29,885.8 meters per second. But what's the centripetal acceleration? Because the radius is so ginormous, 0.00595 meters per second squared, right? Practically imperceivable relative to our measurements here. That's why we don't feel those things, despite the fact that we're moving super fast. Yep.
So if it was like over 9.8,
What's that?
if it was over 9.85 seconds per second.
Oh, yeah, if we were spending, if our day was much shorter, much shorter, we'd feel it. Yeah, sure.